In this lecture, we show how one can obtain a system of finite difference equations for finding an approximate solution to a linear second-order boundary value problem. The boundary value problem is given by the differential equation y double prime of x plus p of x times y prime of x plus q of x times y of x equals f of x, with the boundary conditions that y of a equals uppercase y sub a and y of b equals uppercase y sub b. And so y of x is defined on the closed interval from x equals a to x equals b, where a is less than b. We first partition the interval from x equals a to x equals b using the strictly increasing set of partition points or nodes x sub 0, x sub 1, all the way up to x sub n, resulting in n subintervals. We set x sub 0 equal to a and x sub n equal to b. The numerical or approximate solution that one obtains by this method is a set of discrete points x sub I, y sub I, where I goes from 0 to n. Y sub I is an estimate for y of x sub I. We can use a non-uniform partition, but to simplify the discussion, we use a uniform partition so that x sub 1 minus x sub 0 equals x sub 2 minus x sub 1, etc., etc., etc. And so, the length of the ith subinterval, which is x sub I minus x sub I minus 1, equals the length of the entire interval, which is b minus a, divided by n, for all I from 1 to n. Let the step size h be the length of each subinterval. We approximate y prime and y double prime at each node x sub I using central difference estimates. Y prime of x sub I is approximately y of x sub I plus 1 minus y of x sub I minus 1 all over 2h. Y of x sub I plus 1 is replaced by y sub I plus 1, and y of x sub I minus 1 by y sub I minus 1. A central difference estimate this time for y double prime of x sub I is y of x sub I plus 1 minus 2 times y of x sub I plus y of x sub I minus 1 all over h squared. Y of x sub I plus 1 is replaced again by y sub I plus 1, y of x sub I by y sub I, and y of x sub I minus 1 by y sub I minus 1. We set p sub I equal to p of x sub I, q sub I equal to q of x sub I, and f sub I equal to f of x sub I. We now generate the system of finite difference equations. When I equals 1, y double prime of x sub 1 is replaced by y sub 2 minus 2 times y sub 1 plus y sub 0 all over h squared. P of x sub 1 is p sub 1. Y prime of x sub 1 is replaced by y sub 2 minus y sub 0 all over 2h. Q of x sub 1 is q sub 1. Y of x sub 1 is replaced by y sub 1, and f of x sub 1 is f sub 1. Y sub 0 is y of a, or uppercase y sub a. We multiply everything by h squared. And group the terms according to the y values. For the y sub 1 terms, we have the quantity minus 2 plus h squared times q sub 1 times y sub 1. For the y sub 2 terms, we have the quantity 1 plus half, or 0.5, times h times p sub 1 times y sub 2. We move the uppercase y sub a terms to the other side and get for the right side of the equation h squared times f sub 1 minus the quantity 1 minus 0.5 times h times p sub 1 times uppercase y sub a. Applying the same procedure this time for I equals 2, we get the following equation. Y sub 3 minus 2 times y sub 2 plus y sub 1 all over h squared plus p sub 2 times the fraction y sub 3 minus y sub 1 all over 2 times h plus q sub 2 times y sub 2 equals f sub 2. Multiplying this equation by h squared, we get the following equivalent equation. This equation, unlike the equation for I equals 1, does not involve any given boundary condition, such as uppercase y sub a. We generalize this equation to include the indices I equals 2 all the way up to I equals n minus 2. I equals n minus 2 is the last index whose equation does not involve a boundary condition. For I equals 2 to n minus 2, we have the following finite difference equation. The quantity 1 minus 0.5 times h times p sub I times y sub I minus 1 plus the quantity minus 2 plus h squared times q sub I times y sub I plus the quantity 1 plus 0.5 times h times p sub I times y sub I plus 1, and this is equal to h squared times f sub I. This equation still applies to the index I equals n minus 1, so that replacing I by n minus 1, we have the following equation. Y sub n is y of b, or uppercase y sub b. We move the uppercase y sub b term to the right side, and we get this equation. We now write out this system of equations as a matrix equation. The vector of unknowns is the vector y sub 1, y sub 2, all the way down to y sub n minus 1. The coefficients in the first equation are minus 2 plus h squared times q sub 1, 1 plus 0.5 times h times p sub 1, 0, 0, and nothing but zeros for the rest of the first row. On the other side of the equation is the quantity h squared times f sub 1 minus the quantity 1 minus 0.5 times h times p sub 1 times uppercase y sub a. In the second row, we have the quantity 1 minus 0.5 times h times p sub 2, followed by minus 2 plus h squared times q sub 2, then 1 plus 0.5 times h times p sub 2, followed by zeros all the way to the end of the row. And on the right side is h squared times f sub 2. We continue extracting the coefficients of each y sub I for each of the rows, and we obtain this tridiagonal matrix as the coefficient matrix of the system of equations. We also fill in the vector on the right side of the equation, starting with h squared times f sub 3 all the way to h squared times f sub n minus 2. The last entry is h squared times f sub n minus 1 minus the quantity 1 plus 0.5 times h times p sub n minus 1 times uppercase y sub b.